Okay, so this example, we have a 75 horsepower, 440 volt, three-phase, 60 hertz squirrel cage induction motor, rated to run at its output of 75 horsepower and 850 RPM. And we're also given a full load efficiency of 92%, a power factor of 81.5%. Now, the efficiency here is a bit high and the power factor as well for an induction motor, but this is a fairly large machine, right? 75 horsepower. So, we are asked to calculate slip at full load torque, real apparent and reactive power drawn from the three-phase source, full load current, and we're asked to sketch the power triangle. So, we start off part A by saying that we know the running speed is 850 RPMs. We have not been given the number of poles on the machine, and we have not been given the sync speed, and so we got to figure it out. And so we know that the slip is generally a relatively small number, 4 to 6%, and we have then we should be saying NS here actually is greater than N, not by a large amount. And so there's an inequality that we could go through to write NS, or the number of poles, or we can think about our table. The frequency is 60 hertz, and we know that magnetic poles occur in north-south pairs. So that means that 2, 4, 6, 8, 10, 12, and so on. And NS then is equal to 120 times F, which is 7200, divided by P. And we have 7200 over 2, 3600. 3600 compared to 850, way too high. And so our 7200 here in the numerator divided by 4 poles corresponds to an NS of 1800, still too high. 7200 divided by 6 is giving us 1200. Okay, so we're getting in the ballpark now. 7200 divided by 8 gives us 900. 7200 divided by 10, 720. 7200 divided by 12, 600. Okay, so we know then that N is a bit bigger than NS, not by a big lot, and so that tells us then that our N fits in here. And so we must come to the conclusion then that this is the motor we're dealing with, right? And so according to our table then, we'll conclude that NS is equal to 900 RPM, and that means that P is equal to 8, and of course that means 8 poles per phase. Okay, so then if we're going to calculate the slip, we want to call it S, and slip then is equal to NS minus N for slip speed in RPMs. But when we are asked for slip, we want to, or we should always write it in percent. So we have 900 RPMs, subtract 850 RPMs, which gives us a slip speed of 50 RPMs, and divide that by the sink speed, which was 900. And so 50 over 900 and multiplied by 100 to convert it to a percent. 5 point, and my note says 5.5, but I think we should be rounding that up, right? Yeah, so we should call that 5.56%. So the slip then 5.56%. Okay, part B, full load torque. And you'll notice there that I did not ask for torque developed. This is not a power flow type question, so we don't know PMI. So therefore, we can calculate torque output. And so full load torque at the output, 9.55 times P out, and divided by the running speed, which is N. Now we don't know P out yet, and so I'll go over here and calculate P out. Not that we don't know it, I suppose, but we don't have a value in watts for it that we need. We could put our conversion course directly into the torque formula, but I usually make that a separate calculation, and that's only my own personal preference. 75 horsepower multiplied by 746 watts per horsepower, and the power out then for that machine is 55,950 watts, or 55.95 kilowatts. Now, I mean, you can round that to 56 kilowatts, I guess, if you want to, 56.0. In any event now, if we're calculating torque, 9.55 multiplied by 55,950, and divide by the running speed, which is the number that was given to us at 850 RPMs. And so remember now, this is a bit less than T developed, but it's what we got to work with because we don't have a number for PMI. We just got the machine's rating. And so that torque becomes, if we round to 3 significant digits, 629, and the unit is Newton meters. Okay, now the next part asks us for real, apparent, and reactive power drawn from the three-phase source. Okay, so of course that's input, and in order for us to come up with that number, we got to think about our given information. And so for part C, we'll start off by saying that, look, we got a power out value. And so in order for us to start off then by source, think about our equations, information we've been given. We've been given the rated voltage of the machine. If I scroll back up there for a second. But we don't have any current. In actual fact, we're asked to calculate the current. And so we can't calculate S3 phase as our beginning point. But we have been given the efficiency. And so the efficiency then will relate our inputs, of course, to this power out value, because we know that efficiency is equal to power out divided by power in, and again times 100%. And so if we leave out the 100%, we write our efficiency as a decimal. And so, of course, in this case, 0.92. And so therefore, we can say that the power in will be equal to power out divided by the efficiency. And so, the biggest thing to remember here, of course, is that P in is greater than P out. and so that'll help you get this calculation correct. And so 55.95 kilowatts divided by 0.92. And if you do that calculation, your input power comes out to be, and I didn't round it at all, so 60,815 watts. Well, I guess I did round it to the nearest whole number. And so you can call that, if you want, 60.8 kilowatts. Okay, so we also been given the power factor here, right? And so that means that we can find S3 phase. And so I'm going to move over here now. S3 phase then will be equal to power in divided by the power factor. And again, right, remember that S3 phase is the hypotenuse on the triangle, so it's the largest of the power values, and so bigger than power in other words. So I used 60,815 watts, and I divided that by the power factor that was given. And so remember, 81.5% means 0.815. And so we do that calculation, and we get 74,620. And remember now, the unit is voltamps. And so, you know, I'm not really big on units. If you omit the unit, it's usually not a big deal for me. Where I draw the line kind of for that stuff is, I think the power units are important to help you distinguish between the three different types of power. And so when I give this particular question on a quiz or a test, you know, if you don't include the proper units for S, P, and Q as voltamps, watts, and voltamps reactive, then, you know, there is a mark included in my grading scheme for units on power. And so if you call them all watts, for example, which is, you know, tendency to do, then you'll lose a mark for that, because, like I said, I feel it's important to distinguish between the different watts, the different units for power. And so here we can call this, if we want to, 74.6 kVA. Now, as discussed, you'll find that Q, which is QL here, because this is inductive, and we're told that our power factor was lagging, right? We weren't told that. Well, we can make that assumption because it's an induction motor. And Q then is very often calculated as the third side of the power triangle using Pythagoras' theorem. So S3 phase squared subtract P in squared. And so we get 74,620 squared subtract 60,815 squared, and Q comes out to be 43,240. And so remember, the unit on that, volt amps reactive, and again that is QL. Now, so this is the real power in watts, the apparent power in voltamps, and the reactive power in voltamps reactive, or VARs, that is drawn from the three-phase source. Okay, so one calculation left to do. Part D now is find the current. Okay, so when you're going to calculate the current one of the three-phase power equations is where you should start to. And so S3 phase got one less term. Use P in by all means. S3 phase root 3 times V line times I line. So of course that means the line current is equal to S3 phase divided by root 3 and divided by V line. And so for that, we have then 74,620 volt amps divided by root 3, and our line voltage, which was given as 440 volts. And so that results in a line current of 97.9 amps. Okay, so next is the power triangle. And we know this is an induction motor. So it's a lagging power triangle that we want to draw. And so it points up. Right? And we have down here P in on the vertical QL, and on the hypotenuse then S3 phase, and down here theta. Now, so I've taken the liberty of bringing in a power triangle that I produce with a word processor for me, I guess. And so a little bit neater than my sketch, and labeled with the values that we calculate here. And so you notice that I'm using 60.8 kilowatts, QL at 43.2 kVAR, and S3 phase at 74.6 kVA. And I've calculated theta and put it in there as well. And so, you know, you should always include theta as part of your calculation. And so theta, any of the trig identities can be used to calculate theta. And I always use this tangent because I found that if you calculate the same way every time, you're much less likely to make a mistake. So it's the inverse tangent of the vertical component, which here is QL, divided by the horizontal component, which here then is P in. And it don't matter if you're applying that to an impedance triangle or a phasor diagram, right? Tangent is always the vertical component over the horizontal component. And so the inverse tangent of 43.2 divided by 60.8. And of course, you know, we could use the 43,240 over the 6815. Not going to make much of a difference to our calculation there. And that gives us well, I got 35.4 degrees for that. And that is a lagging phase angle. And so that means that I got a mistake, I think, on that triangle that I brought in, because that number there is not correct. 35.4 degrees. And so now, let's think about that, right? QL is smaller than PN, and so that definitely means that our angle is going to be smaller than 45 degrees. And so the 35.4, I suspect, is the correct number for that. And well, you can check the math with your calculator, of course, no problem.